Hello friends, it is Ben again, and I'm here to do a video for vector calculus. The video in question is about flux integrals. Your textbook will refer to them not as flux integrals, but rather as integrals over vector fields. Same thing. And if it turns out that I'm using the wrong term for it, please somebody tell me so that I will quit looking like an absolute fool in front of everybody. So I will look like less of. All right, anyway, so the essential notion here is that you are going to have your integral across a surface, and you will have a vector field F, and it will dot with ds vector. And by that ds vector, what you will put in there is somewhere or another noted as an in vector. And then the in vector will be a t sub u cross t sub v, and then du dv. Okay, all that stuff should make you shudder in fear, because you're just going to be certain that you've got to do all the unit vector crap again. But the du dv, because it's got the Jacobian in it and blah blah blah, it all means that you will, for your t sub u and t sub v, just be taking the derivatives and just take the cross product. So remember the thing that I had y'all doing in the previous section with if it was parameterized as g vector, then g sub u cross g sub v? Same thing here. Except now you don't have to take a magnitude, because you're going to take a dot product of something. So benefit on that. And then there's another nice bit. Oh, and then the other bit is you have to pay attention to the orientation of the surface. What we mean by the orientation of the surface is which direction is up. Okay, so probably best to go ahead and share screen here and show you my little sketch where I tried to illustrate what's going on with this. All right, so your flux integrals are going to be across some surface, and there you see I've tried to draw a surface, and I just went ahead and at some point on the surface drew a unit vector. And so at the point in consideration, you've got both the unit vector and the flow, or the vector field, that you're dealing with there. And because you want to talk about the amount of flow that is in the direction perpendicular to the surface there, you take the dot product between the n vector and the f vector. Okay, so yeah, so when you figure out your n vector, it needs to point in a particular direction, and you get it by doing your g sub u cross your g sub v. But then if your directions say that a particular way is the orientation of the surface, then you need to take a look at your g sub u, g sub v, and visualize it in order to see, is it pointing the right direction? So typically with this, it'll have something like the positive z direction, the negative y direction, but you might also see something where it wants you to have something pointing up and it's a curved surface, or something where it wants you to have something that's cylindrical and it points out. So with regard to that, out is going to be the direction that's r cosine theta, r sine theta, and then 0, I guess. For up, then, or down, that's going to be that the z entry needs to be something that's positive. Okay. The other tricky bit is illustrated here, because we say a double integral of the f vector dot ds vector. And when we do the actual integration, it will turn into a double integral du dv. And you have this here that just means the domain that you need to talk about. So if you're talking about, say, a something that is parameterized as though it were a disk with R's and thetas, then that's D for the domain is going to end up being, you know, your R between 0 and 1, and your theta between 0 and 2 pi, or whatever it happens to be. However, please realize that it sometimes takes a little bit of work and a little bit of experience of having done these to see what that D is going to turn out to be. Okay. All right. But in essence here, you've got your vector field that's got an X, Y, and Z, and then the X, Y, and Z are going to be given to you by a U and V in a parameterization. And we have to be willing to make some switches this way and that, and use different variables, whatever is appropriate for what we're working with. Okay. So we're going to take a look at this one here, which asks us to compute that flux integral. And it gives us an f that has permuted the x and y and z coordinates. And then our surface is going to be given by 3x minus 4y plus z is equal to 1. So a plane, but with the x's and y's going from 0 to 1. Okay. So we've got something plane like. I am not making an attempt to get this to point exactly the right direction or anything. But the nice thing here is that for that n vector, it's going to be constant. And in fact, you could get away with not doing the cross product stuff in order to get that n vector, because you can see that it's going to be 3, -4, 1. Okay, and that's just from being able to read off of a plane equation there, right? But we will need to think a little bit about our parameterization, and I'm going to write this as just g of xy. I'm not going to try putting in a u or v. If you want to, you can, but it doesn't really help that much. I'm going to put an x and a y here, and then the z is going to be 1 minus 3x plus 4y. So when we talk about getting our unit normal vector, we'll calculate a g sub x, 1, 0, -3. We'll calculate a g sub y, 0, 1, +4. And then that g sub x cross g sub y, I did this ahead of time, 3, -4, 1. Notice the instructions here said that we wanted the unit vector to be pointing upward. And since that has a +1 in the z direction, it does. Okay. But again, you could have just read it off of that portion there. Okay. The reason I said that we needed to say something about the g of xy is really so that you can see what the x and y are if you have the parameterization. Yes, maybe not all that necessary here. Since our f vector, we would have the y, and then the z, the 1 minus 3x plus 4y, and then the x being just the x, then our integral for the surface f dot ds vector will be integral. Notice that it said the x's and y's both go from 0 to 1. And then we would have to take the dot product here, y 1 minus 3x plus 4yx dotted together with 3, negative 4, 1, dx dy. So we're doing an integral 0 to 1, integral 0 to 1. And let me see what that dot product turns out to be. I think after you simplify it, it should turn into 13x minus 13y, and then minus 4 dx dy, or dy dx, whichever direction you want to do that in. And so we'll integrate there. That 13x with respect to x is going to end up being 13 halves x squared, and then you evaluate 0 to 1, so we will end up with a 13 halves out of that, minus a 13 xy, x going 0 to 1, and then a minus 4x, the x going 0 to 1, and then we'll have that reduced there. We can put this piece here together. Let's see, 13 halves minus 4 is going to be 5 halves. So we're really doing integral 0 to 1 of 5 halves minus 13y dy, which will be 5 halves y, evaluate 0 to 1, and minus 13 halves y squared, evaluate to 0 to 1. So we end up with minus 8 halves, which is negative 4. All right. So the actual integration portion of this, not going to be too terribly rough to deal with, hopefully. But the setting up and stuff sometimes takes a little bit of imagination to get it put together. Okay. All right. Let's take another look at another one here. And this one, the f we've got has xy, comma y, comma 0. Now that's kind of nice to have that 0 in there, because when you take the dot product, it's going to wipe out one of the entries, right? But the s is z squared equals x squared plus y squared, which tells me that we've got a cone opening up and down. But this one says in particular that we've got the z being greater than or equal to 0. So that says that our cone doesn't open both directions. It just goes upward, okay? The x squared being less than or equal to 4. I'm sorry, the x squared plus y squared being less than or equal to 4, we're going to read as saying that the domain space is going to have a disk with a radius of 2, okay? So with our setup here, the G, I'm going to go ahead and do it with R and theta. So R cosine theta, R sine theta, and then the Z, notice over here we have Z squared equals x squared plus y squared. Well, that means Z squared equals R squared, so Z is equal to R. So now we'll do our G sub R and have cosine theta, sine theta 1, and our G sub theta will have, let's see, minus R sine theta, R cosine theta 0 here, and then the G sub R cross G sub theta for that. What was that? Again, I did this ahead of time. And so when you do that, you come out with R cos, no. Yeah, I did it ahead of time, but I can see that I have an algebra error in what I did ahead of time. Okay, so the cross product there with the G sub R cross G sub theta, we're going to have to say sine theta minus R cosine theta. So minus R cosine theta, and then minus R sine theta minus 0. That's R sine theta, comma, and then we'll have the R cosine squared minus a negative r sine squared. So that means we end up with an r here. Oh, haha. As it turned out, I didn't make an algebra error. It's just that I don't have what I want. Notice here that I'm supposed to be getting an n vector to point downward. This n vector points upward. So what I really wanted was going to be g sub theta cross g sub r. But I don't have to rework this. I can just say this is the negative of it, because the negative would be the g sub theta cross g sub r, and multiply everything through by a negative. Remember that when you change the order of a cross product, that it will change the sign there. All right, so grab all that, push it over to the side a little bit there. And the f that we want needs to have an x times y. Well, that's going to be r cosine theta times r sine theta. So I'll write it as r squared cosine sine, comma. And then the next entry is just a y, so r sine theta. And then the last entry was a 0. So we need to set up our integral here. And I'm going to put the theta on the outside. Since we wanted the full round of the circle there, we'll go 0 to 2 pi. And since it wanted the x squared plus y squared less than or equal to 4, the r will go 0 to 2. And then I will need to say r squared cosine theta sine theta, comma, r sine theta, comma, 0, dotted with the r cosine theta, r sine theta, minus r dr d theta. Okay. And so when you take that dot product there, you will end up with an r cubed cosine squared theta sine theta, and then plus an r squared sine squared theta, and then a plus a 0, but dr d theta. Okay. And now we'll have to do the integration with respect to r in there. And the nice thing is it's just a power rule, right? So when you integrate that with respect to r, you will end up with a 1/4, and then the r to the 4th, so you end up with a 2 to the 4th cosine squared theta sine theta plus 1/3 r cubed, so 2 cubed sine squared theta, and then a d theta, because we're going to subtract a 0 in there. Okay, so now we have to do integral 0 to 2 pi of, let's see, 1/4 times 2 to the 4th, 2 to the 4th is 16, so 4 cosine squared theta sine theta plus 8/3 sine squared theta d theta, oh, close parentheses, d theta. Now, I'm going to make a quick point here if you have to integrate bunches and bunches of sines and cosines. If, for example, you ever have to do Fourier series stuff, there's some tricks about integrating 0 to 2 pi for sines and cosines. Here, with this one, you would end up doing a u sub, where the u is going to be equal to cosine of theta, and the du would be minus sine theta d theta. And that means when you substitute in the 0 and the 2 pi, they cancel out. And so we end up getting 0 out of that. But when you integrate an even power across the interval, it doesn't turn out to be 0, because you have something that's all positive. It's not going to be positive and negative in order to cancel out. So the integral from 0 to 2 pi of sine squared theta or cosine squared theta, either one, turns out to be equal to pi. Okay, that's something that you should know from Calc 2. If you don't happen to remember it, it's totally okay, but write it down somewhere because it comes up enough that you don't want to have to type that crap into Symbolab or something to do the calculation every time. It's just, it's worth knowing that when these integrals turn out to be 0 and 2 pi, and that you can skip some steps. Okay. All right, so we ended up with 8 pi over 3 for that one. All right, so this is another sort of problem here. The notion is that you've got a membrane with a certain shape, okay? So that's going to be a parabolic sort of shape. Since we said the y is going to be greater than or equal to 0, then that means that the x's are going to be such that the y goes between 0 and 1. So if you wanted kind of a graphic representation here, we would have something like that. And I don't know whether I can make hidden lines here or not. Yeah. So you've got a membrane that looks somewhat like that. Maybe it's a net, but it could be, you know, some other kind of shape as well, or some other kind of application of a membrane as well. I believe that I actually have one of your homework questions has something like a net being dipped into a river or something like that. Okay, so the shape that we've got here is going to have one of these circular domains, right? That minus x squared minus z squared sort of thing that's showing up there. So when we set up our parameterization for this, I'm going to put r cosine theta on my x, but not on my y. My y is going to end up being 1 minus r squared, and my z is going to be the r sine theta. Okay, so now when you do your g sub r, g sub theta, since we did something like this just a minute ago, we might know which order that we want to do this in. The instructions say we want to have the orientation in the positive y direction. And when we did g sub r, g sub theta before, g sub r cross g sub theta before, we ended up with a negative showing up there. So I'm actually going to write down g sub theta first. And then you have to remember how to take derivatives, which is sometimes a little bit of a hard thing for me. And we end up with that. And then our g sub r, we have a cosine theta, a minus 2r, and a sine theta there. And then g sub theta cross g sub r. To see what we end up getting there, we should end up with a 2r squared cosine theta and an r and a 2r squared sine theta. Okay. All right. Then it's also helpful here to be able to say what our f is in terms of the r and theta. And the f that we're going to look at, let's see, x minus y. So r cosine theta minus, and the y is 1 and minus r squared, and then z plus y. So r sine theta, and then plus 1 and minus r squared. And then the z squared is going to be r squared sine squared theta. Okay, so it looks terribly messy there, but now we're going to have our integral set up, I'm going to put the 0 to 2 pi on the outside, the 0 to r, 0 to r, what am I thinking? The 0 to 1 on the inside. And then we get to think about this horrifying dot product. Okay, r cosine theta minus 1 plus r squared comma r sine theta plus 1 minus r squared comma r squared sine squared theta. And then we have to dot with, oh my, I have to hold that back farther so we can write it all down. 2r squared cosine theta or 2r squared sine theta, dr d theta. Woohoo, right? So then the thing that we have to integrate here, goodness, this is going to be such a mess. Integral 0 to 2 pi, integral 0 to 1, and the setup here, I have notes out to the side for this, so 2r squared cosine theta or cosine theta minus r sine theta plus r times r sine theta plus 1 minus r squared plus 4. Oh, for goodness sake. Y'all, I forgot to write my plus 4 up here, which is why that looks wrong. Okay, and then plus, where was I at? 2r squared sine theta, and then an r squared sine squared theta. And that dr d theta. Boy, that's pretty messy, right? No way we're going to finish this on the same page. So let me make a copy. We'll go to the next page. I will paste it and move it so that it's all in one line, I hope. Okay, so now we have to go ahead and pull that apart in order to see where everything's going. Let me see whether I can write this down correctly. Y'all watch and make sure that I get this right, because if I don't, I'll have to come back to it. Plus r squared sine squared theta plus r minus r cubed plus 4r plus 2r to the 4th sine cubed theta dr d theta. All right, let's see here. I don't see anything I can combine. Great. Oh well. Although I do notice that I forgot to write my integral with respect to r there. Integral 0 to 1. All right. So going through here, we're going to use this trick again. When you integrate a polynomial, this r to these various powers, between 0 and 1, you can just take and drop the variable part and divide by the new power. Okay, so that means that this 2r cubed becomes just 2 divided by 4. Cosine squared theta minus 2 divided by 4 sine squared theta plus 1/3 sine squared theta plus 1/2 minus 1/4 plus, oh, there's some things that can be combined. Oh well. 4 halves and plus 2/5 sine cubed theta, d theta. All right, so is there any of that we can tidy up? I mean, this piece right here all goes together, and this piece right here will go together. But other than that, yeah, 1/2 cosine squared theta minus 1/2 and plus 1/3, so minus 6 sine squared theta, and gosh, 5 halves minus 1/4, so 9/4 plus 2/5 sine cubed theta, d theta. All right. And now we're going to use our tricks about integrating 0 to 2 pi on powers of sine and cosine. And when we integrate this one and this one across 0 to 2 pi, we will end up getting pi. So we'll have 1/2 pi minus 1/6 pi plus 9/4. Now that one will just get multiplied by 2 pi because it didn't have any sines and cosines with it. And then this one here, you would do you would change that into sine squared times sine theta, and then do a u substitution, and you'll end up getting 0 out of it. So then, what do we end up with? Pi over 3 plus and 9 pi over 2, which is, I should probably be embarrassed that I can't do that in my head. Uh, 29 pi over 6. Okay, so terribly messy, but doable. All right. Okay, so here is the problem that looks the most intimidating and turns out to not be too bad, right? So these Faraday's law sort of problems, I will leave it to the physics folks to explain the exact thing that's going on. But you end up getting a relationship between a line integral that is the line integral around the loop here of an electric field. And it turns out to be equal to the surface integral, with the surface being the rectangle that the loop describes there, or the loop encloses there. But the surface integral of the magnetic field, okay? Now, the magnetic field that is induced by this electric flow going down here, we're always trying to set it up so that the electric flow is going down the positive x-axis. And then we'll have to see, where the x and y axes are in setting up our rectangle in this case. But once we've got that set up, the thing is going to be that we will end up having that the direction of flow is, for this setup, is going to be in the positive z direction. If you think about taking x cross y here, then you should get the z-axis as the result for that. So then the big thing that I didn't know without having to look it up and stuff, was that the B we're talking about is going to have a magnitude given by some mu sub naught times the current that's running down the wire, divided by 2 pi times the distance up to the point that we're looking at the field being at, okay? So with the setup we've got here, the current is going to be this 28 cosine of 400t. Notice there's no x or y in that. That's not something that's going to vary um, with its position that we've got here on the x-axis. So that part's fine. But it flows down a wire, and the distance of the wire is going to be 0.1 meters from our rectangle. Okay. So we're going to set this up here and look at it as though we've got our, yeah, bear with me as I draw it out here. Okay, so we're going to have our rectangle set up like that. I doubt that my units turned out right at all, but length is going to be 1.2 meters. This is going to be at 0.1 meters up there, and then this 0.7 meters higher. So this will be a 0.8 at the top of it. Okay. So when we set this up to calculate this flux, and I naturally have not written this anywhere, but we are needing to calculate the double integral across its S for surface, but maybe I should be putting R for rectangle. Yeah, so S, and then it's B dot, well, B dot the ds vector. So what we have to spot here is that our B is given to us like this, which is kind of messy, but we can deal with it. So we'll have an integral. We'll have to set up our limits here in a minute, but the limits are just going to be that rectangle. And then the B needs to have a mu naught, and the I is given to us with this 28 cosine 400t, with then divided by, what did it say there? 2 pi y, and then the n vector. But then with our ds vector, we're going to get the n vector again. And that n vector, of course, in this is actually the k vector. But anyway, and then we'll say dx dy. Okay. And I'm going to erase that just to get it out of the way. But then we have to say where does our x go between? And we look back at our little diagram here or a diagram here. And we see that that length went from 0 to 1.2 meters along there. And then we have to look at our y portion, and it goes up here, or it goes up here, either way that you want to look at it. And so it goes from 0.1 up to 0.8. And be careful about that, because that's something that I just keep dropping terms on, you know. But now that we've done that, we get this integral 0.1 to 0.8. Oh, no. That's there's no need to be messy. All right. So notice all this mess in here. This is all the y that there is to it. So if that's all the y that there is to it, just pull everything else out. So you will have a mu naught. Get a 28 cosine 400t. I'm going to go ahead and cancel the 28 with the 2 and have 14 cosine 400t, and then I'll divide that by the pi, okay? And then we'll have to integrate 0.1 to 0.8. Did you notice there's no x's in there? right? So that means I've got just a 1 over y dy, and then my 0 to 1.2 dx. I can pull those apart because there's no x's appearing at all. So that means I just end up with a 1.2 out front, mu naught 14 cosine 400t all over pi, okay? And then a logarithm of y going from 0.1 to 0.8. And so 1.2 mu naught 14 cosine 400t divided by pi. And now I can say log of 0.8 minus the log of 0.1. But all of y'all remember this law of logarithms and stuff, right? That when you subtract two logarithms and they're the same base, that you could combine that together and turn it into the log of 0.8 divided by 0.1, so log 8. So you can get an actual quantity then for that. And then, and I have to confess to y'all that this is an example worked out in your textbook. Your textbook then says that mu naught equals 4 pi times 10 to the minus 7th. I don't know, Claire, why you know that. But if you have what that mu naught is, then you can plug that back in there and get your actual units right and stuff. And looking at the example in the textbook, they end up with 1.4 times 10 to the minus 5th cosine 400t, and the units are t times m squared. So the m squared is meters. I don't know what the t stands for. So Teslas, I guess. So, all right. So if you take a look at that one, it looks horrifyingly complicated, but it's the physics that's complicated, not the actual math end of it. So anyway, I'll have some problems like this for y'all tomorrow morning. Come ready to rock and roll, and we'll get these worked out. All right. I'll see y'all then.